In Part 2 of Lecture 4, we will discuss scheduling processes. When a new process is created, it is originally placed on a job queue. The computer can only juggle so many processes at a time, and we cannot assume that it will be able immediately to make this one active. If it can, it will load it into memory and place the process on the ready queue so it can get its first use of the CPU in due time. However, if there is no more room for one more active process, it will sit on the job queue and wait there. As soon as there is room for the additional process, one will be loaded into memory and placed on the ready queue. Eventually, the processes on the job queue will work their way to the front of the job queue and become active. Once active, processes enter a cycle where they have the use of the CPU until they either schedule I/O and have to wait for it to be completed, or time out and have to wait for another turn in the CPU. The basic cycle is execute and wait, execute and wait. This continues until a program finishes and terminates, or is aborted for whatever reason. The ready queue is not the only queue on which processes sit. When processes are blocked, they are generally waiting on device queues until whatever input-output operation they are waiting for is scheduled. After the I/O operation is complete, they will then wait for the CPU again. Generally, processes spend their time either waiting or actively engaged in the CPU or I/O. If this is not the case, usually the process is suspended. The job queue that we spoke about a moment ago is the handiwork of the long-term scheduler. This is usually the case in a batch system, where a large number of processes may be entered in a short period of time. In a batch system, programs being entered are stored within the spool system. It is the responsibility of the long-term scheduler to decide which processes are loaded into memory and placed on the ready queue. The short-term scheduler, on the other hand, is responsible for deciding which is going to be the next process to get the use of the CPU. While the long-term scheduler controls the degree of multiprogramming, the number of concurrent processes that the system will juggle, it executes far less frequently than the short-term scheduler. Since the short-term scheduler executes fairly often, as in every time a process is switched out, it must be fairly quick. It is important to remember that all of the operating system's operations are overhead, and that however necessary they may be, they are not considered as important as the processes that they schedule and support. There are two main activities in which processes will engage: computing using the CPU and in performing input-output. Processes, depending on the kind of application, will spend more time engaged in one of these two activities than in the other. CPU-bound processes spend far more of their time making active use of the CPU. Numerical applications are a good example of this. For every item that they print, there will be a large number of calculations that will be performed. These will need huge amounts of CPU time compared with other processes. The other processes are processes that are more involved in reading and writing data than in using CPU time. Most traditional business applications, such as report generation, belong in this category. These are called I/O-bound processes because they spend most of their time waiting for input and output, and these operations are inherently more important than the use of the CPU. While they do not typically need much CPU time, it is more important for them to have quick access to the CPU so they can get back online and wait for the next I/O operation. As we will see later when we discuss process scheduling, recognizing the different needs of CPU-bound and I/O-bound processes is important in devising scheduling algorithms. Many systems will have a third type of scheduling. Some systems can juggle more processes than they have stored in physical memory at a time. This requires the operating system to swap processes in and out of physical memory. This extra stage is known as medium-term scheduling because it happens more often than long-term scheduling and less frequently than short-term scheduling. Processes that are ready, running, or blocked are all active. They are either using the CPU, waiting for it, or in the process of performing input-output. But sometimes it is necessary to suspend processes. This can be for one of a few reasons. Perhaps the system is overloaded enough that it is in danger of crashing. Perhaps this process has a low priority, and we wish to expedite other processes. Perhaps the process's output seems potentially incorrect, and we wish to see if it is running correctly. Any of these reasons may be sufficient cause for suspending a process. The only question is whether we have to wait for it to be ready before suspending it. We may wish to suspend a blocked process to ensure that a system crash doesn't happen. If we wait for I/O to be completed, it may be too late. In either case, this adds 2 additional states in which we may find our process. But we expect that running, ready, and blocked are the most common. Something has to suspend a process. On a one-processor system, it would have to be whatever process is currently controlling the CPU. A process could suspend itself, or another process could suspend it. In a process-oriented operating system like Unix, another process would have to resume a suspended process, which obviously could not resume itself. While it might be better for a process to be suspended after rather than before its I/O is completed, this may not be possible, especially if the system's overload is likely to cause a system crash. Therefore, it is in the system's and process's best interest to allow a blocked process to be suspended.